so that's fine. I'll take it from here. Happy to introduce Hadi Charkhgard, who's on the faculty in industrial engineering at the University of South Florida. Hadi's done lots of kind of interesting work in the recent years, particularly in a very difficult problem of multi-objective integer programming. And so there's been lots of developments there based on his work and multiple algorithms. And so today, I think he's going to tell us about a different perspective on this kind of problem from the Nash welfare optimization viewpoint. So Hadi, please go ahead.
Yes, thank you very much for the nice introduction. And also thank you very much for inviting me to this series of talk. I think this is a really nice effort to make the kind of community connected through these challenging times. So let me take this as an opportunity and try to advertise Informs Computing Society Conference 2021, which is going to be in Tampa, Florida in January 2021. Hopefully these challenging times are going to be over by the end of this year. And I hope that I can see all of you in January 2021 in Tampa, Florida for this conference. And so down January is going to be a really good time to visit Florida, by the way. Today I'm going to talk a little bit about a program that I call it Nash Social Welfare Program in optimization. And the message of my talk is going to be, please do not sum and try to always multiply. So that's the message that I'm going to give. So my talk is going to be very broad, and then I have lots of backup slides, and if necessary, I can go through them to provide more details. So I would like to thank all the collaborators that I had over the years, and I have put a subset of the collaborators here, and so all of these works were not possible without them, for sure. So let me, right at the beginning, so I'm not sure why my slides doesn't. Okay, so let me right at the beginning give the conclusion of my talk. The conclusion of my talk is that it's really good to redefine any optimization problem in the following form, in the form that I had, that you can see on your screens. Basically, you're going to maximize the product of some non-negative decision variables to some non-negative powers. All the powers that you see, WIs, are going to be non-negative here. So I started to work on this problem in 2013 when I was a second-year PhD student. And at that time, I just felt that these type of optimization problems are cool. So that's why I started to work on that, because I knew that at that time that these type of optimization problems, they have applications in maximum likelihood estimation or systems reliability or this type of things. But over the years, when I was working on this problem and trying to develop some algorithms for that, I realized that actually you can transform any optimization problem into this form, and you can get some interesting results. And hopefully today I'm going to convince you that if you change your problem into this form, it's going to be a good idea. So in order to do that, I try to, at the beginning, I try to introduce my notation for single objective optimization and multi-objective optimization. And then I try to tell you a little bit about the challenges and weaknesses that you may face in practice when you're dealing with this type of optimization problems. And then I'm going to tell you how you can transform any single objective or multi-objective optimization into this form. And then finally, I'm going to briefly tell you a little bit about how you can actually solve this problem, okay, using the existing state-of-the-art techniques. With that, I should also tell you that I explained a little bit about this type of formulations in one of my classes in 2017. And since then, just in the University of South Florida, we had like 10 or 15 publications from different engineering disciplines that they use this optimization kind of programs in their research, and they got some results there. So from healthcare to transportation to power and this type of things. Okay, with that, let's talk a little bit about the single objective optimization. Single objective optimization, without loss of generality, I would like to introduce this notation for that we want to maximize some weighted summation of arbitrary functions over a feasible set. So my assumptions is that this feasible set is going to be bounded. So that's the first assumption that I'm going to make. And the second assumption that I want to make is that all the weights that you see in the objective function of these single objective optimizations are going to be strictly positive. So now you can see that probably this is almost any single objective optimization problem can be written in this form, right? I'm not going to tell you how you're going to create these arbitrary functions fi of x, because that depends on the application that you are dealing with. So you have a lot of flexibility in defining this fi of x in any arbitrary way that you want. However, the way that you are defining this fi of x, it's going to impact your Nash Social Welfare Program that I'm going to introduce for you later. For obvious reasons, I sometimes call this single objective optimization as a weighted social welfare program. Okay, to me, single objective optimization and weighted social welfare programs are the same thing. Okay, so this is my notation for multi-objective optimization. I want to maximize some weighted. I want to maximize a bunch of functions here for you. S plus is the set of functions that I want to maximize, and S minus is the set of functions that I want to minimize. Okay. So this is the multi-objective optimization. Okay. So now, given that we have introduced these notations, I'm going to tell you a little bit about what are the challenges when we are facing a single objective optimization and multi-objective optimization in general, right? So let's start with the multi-objective optimization, and I'm going to give you two weaknesses for that, right? So in general, when we have a multi-objective optimization problems, the main goal that is in our mind is generating some or all efficient or Pareto optimal solutions. Okay, so so this is your basically multi-objective optimization program that you have, and let's see what is the Pareto optimal solution for a moment. Suppose that you have two objective functions that you want to minimize. Here I'm assuming for the purpose of illustration that you don't have any objective function that you want to minimize. So you have two objective functions that you want to maximize. Okay, so these points that I have drawn here for you, they are Pareto optimal points. The reason is that if you choose any of these points, for example, this point in the middle, then you can draw a box that we call this box as a domination box, and this box is empty. So that means that there is no solution that if you plot that into the criterion or objective function space to be in this box, okay? So in other words, whenever this box is empty, whenever the domination box is empty and you have a feasible solution, that means that that feasible solution has to be a Pareto optimal solution, okay? That's what it is. So now let's see how we can deal with a multi-objective optimization in practice. Okay, so whenever you have a multi-objective optimization in practice, so at the end of the day, you need to select one of these Pareto optimal solutions, right? And because you want to implement them. So how are we going to select this desirable Pareto optimal solution? We can do it in two ways. Okay. There are two common ways of doing that. One way is that we can generate the entire Pareto optimal solution first. We can generate it first, and then we can pass it to the decision makers or managers, and they can select one of them. Okay, so that's the approach number one. Another approach is that we can make it interactive. What does that mean? That means that I can first find one of the solutions, Pareto optimal solutions, and then I can ask my manager, are you happy with this solution? And then she may say that, look, no, I'm not happy, just go and find another thing. So I'm going to go and then find another solution in the direction that she has provided. I'm going to come back. And I'm going to do this iteratively until we actually converge to a desirable Pareto optimal solution. Okay, so there are two different approaches that you can do. Okay, so these approaches are really, really good, and they work in many practical scenarios. However, they have an issue. The first issue is that in some practical solution, computing even a single Pareto optimal solution is computationally invisible or expensive. So it takes a lot of time for us to compute a single Pareto optimal solution. So whenever you're in this setting, both of those methods that I mentioned to you, they're going to be useless because you cannot implement them. You cannot even find one Pareto optimal solution. Okay, now you may say that in these particular scenarios, we can just go out and try to use heuristic algorithm to create some Pareto optimal solutions, and we can work with that. So yes, that's a possibility. However, the issue is that there is no quality guarantee in doing so. Another weakness is that you can see in sometimes that in practice, there is no decision maker. There is no final decision maker. Or the decision makers themselves cannot choose a desirable Pareto optimal solution. Especially this scenario happens when you have a lot of objective functions that you want to deal with. Then the situation with the decision-making process is going to be very tough for managers to select which solution is going to be desirable. Okay, so okay, with that in our mind, so we should find an alternative way. So what is an alternative way? The alternative way is that we need to somehow balance the conflicting objectives somehow for the managers, right? So we want to find a solution that can balance the conflicting objectives in a desirable way. So right at the beginning. Okay, in order to do that, you can see that, for example, if you have this Pareto optimal frontier, obviously the endpoints are not going to be very interesting because they are extreme solutions. However, something in the middle is probably going to be more interesting because they can balance the conflicting objectives better. Okay, so have this in your mind. So we're going to say, I'm going to show you that the Nash Social Welfare Program is going to do that for us. It's going to find a solution that's going to balance the objectives, conflicting objectives in a good way. Okay, so now let's move to the single objective optimization. I'm going to tell you two main weaknesses of single objective optimization in general. First, I want to show you that whenever you are solving a single objective optimization, believe it or not, you are actually solving a multi-objective optimization. Okay, you can view your problem from the angle of multi-objective optimization. Okay, so here's the definition of multi-objective optimization that I gave to you earlier. Now, I can multiply the minimization function by -1 to get a maximization function, and then I can add them together with some weights, and then you have your single objective optimization that you have. So any single objective optimization is constructed from the multi-objective or it's basically a multi-criteria optimization problem that you try to solve it, okay, by aggregation. So you try to solve a multi-criteria optimization by aggregation of the objective functions. Okay, so these type of aggregations are really good in many practical situations. However, they have some weaknesses. Okay, whenever you're aggregating some conflicting criteria, so you need to always ask yourself that, okay, do I get a desirable Pareto optimal solution in this way? The solution that you're going to get from this single objective optimization, does it going to balance the it's going to balance the conflicting objective functions or not? So this is a question that you need to ask. Okay, and I'm going to tell you that in many scenarios, this is not going to happen. So for convex optimization problems, probably that's going to be the case. However, for the non-convex optimization problem, there is a high probability that this never happens. Okay, so so consider this particular example that I gave to you right at the beginning. So if you use a single objective optimization transformation, you can only remember the objective functions here are maximization objective functions. In this case, you can never find any point in the middle by any weights that you want to consider. So it doesn't matter what weights you consider, you always want to end up to one of the endpoints of the frontier. So anything in the middle will be missed. And by the way, those points that they were in the middle, they were more interesting to us because they were conflicting the objective functions better for us, okay? Not the extreme points. So these points that we cannot find, we call it unsupported Pareto optimal points. And they can be, for non-convex optimization problem, you can have infinite number of unsupported Pareto optimal points that you cannot find. Okay. Another weakness of single objective optimization problems is that whenever you're solving a problem of this form, so in some scenarios, you are in a situation that these fi functions, these little criteria that you have in your mind, are for independent players, independent entities. Okay, so whenever, so basically, when you are solving a single objective optimization of this form, you are trying to coordinate independent entities, independent players of your game, right? So you want to find a solution that everybody feels happy about it. So, okay, so if you're trying to find a solution that makes everybody happy, then that means that you should always ask yourself that by solving this optimization problem, do I achieve fairness? Okay, I will define exactly what I mean by fairness later in this talk, but let's for now, let's look at the fairness in a broad kind of sense. Okay, so let's look at this example that we had here. Suppose that F1 belongs to one independent player, and F2 belongs to another independent player, and we want to coordinate with them, right? So if you use a weighted sum, I know that I cannot find any endpoints of the non-dominated. I can only be in one of the endpoints. I cannot find anything in the middle, right? Okay, if we're going to end up to one of the endpoints, then of course one of the players are going to be very unhappy, because those points, in terms of utility functions, it's not going to bring much for them, right? So perhaps the only fair point of this game is the point in the middle, 3.25 and 3.5. This is the problem, the fair point of the only fair point of this game that can make both players happy at the same time. So you can see that weighted sum or social welfare program cannot ensure fairness for you, and that's another weakness of the single objective when you are dealing with the single objective optimization problems. Okay, now let me give you a practical example. I know that the second speaker has also worked on this topic for quite a long time, so let me give you a little bit of kind of explanation on in one practical example that I faced in the last 2 or 3 years that I was working with the United States Geological Survey. So people that they are working on the field of conservation planning, one of the problems that they normally deal with is called reserve design problem. In the reserve design problem, the question is that which sites or parcels should be protected within a geographical region to preserve biodiversity. This is the question that they normally ask from themselves, right? So in this particular scenario, they have a set of parcels. They want to identify on which parcels they need to spend money. And they have a bunch of endangered or important species, right? So this is S+. And they have a bunch of species that they are invasive. They don't like them, so they want to hopefully get rid of them as much as possible. And so you can, for this type of problems, you can have lots of constraints, but one of the typical constraints is a knapsack constraint that you will see. They have a budget, they want to make sure that they're not going to violate this budget. They can face some other types of constraints. For example, they want to select these parcels in such a way that these parcels to be connected with each other so that the animals or species can walk from one parcel to another parcel easily, or sometimes they want to make sure that these parcels create or form a compact shape. So you can come up with so many other constraints that I'm not going to go through them. This is a simplified version of the problem. Now, if you acquire each of these parcels, then you're going to have an impact on a species, on each species. So for example, you can consider the impact as an increase in the population size of that particular species. So in that case, you can define your little x function as the basically growth rate of that particular species. Okay, so this is a general setting. Now suppose that I ask you to please solve this problem. So whenever you're trying to solve this problem, people normally end up to two particular kind of they're going to use two particular approaches. One is the single objective optimization. The other one is a multi-objective optimization. Okay. So the issue is that if you go with the multi-objective optimization, multi-objective version of this problem, the number of species can be really large. If the number of species can be really large, then your decision maker is going to have a problem in selecting the desirable Pareto optimal solution. Also, you may have lots of constraints and lots of binary decision variables to deal with, and in that case, finding a single Pareto optimal solution may become difficult for you. Okay. So if you transform it into a single objective optimization in the way that I mentioned and try to solve a social welfare program, then the problem is that you're not going to find unsupported Pareto optimal points, and that's bad. So because this problem is non-convex. So alternatively, one of the things is that if you change it to a single objective optimization, you can view each of these species as an independent player in your environment. So when you're transforming your problem into a single objective optimization, you're basically trying to coordinate these independent species or independent players, right? And then you want to find a fair solution for all of them, right? So we know that this single objective optimization problem may not achieve that. Okay, so that's a problem. Okay, so how should we solve this problem? I say, okay, what we are proposing is the approach that I'm gonna tell you. So that we call it as a weighted Nash Social Welfare Program. The weighted Nash Social Welfare Program is basically a program that tries to coordinate or try to create a coalition between independent players, right? So this is a Nash Social Welfare Program. We are trying to maximize the product of our function from a reference point. So the difference between the reference point and the utility value of each player, it's the benefit that the player will get. So we try to maximize this point. Of course, any player would like to get a value larger than the reference point. What is a reference point? The reference point is the status quo of the system, right? So it's a point that says that, okay, if the players do not cooperate with each other, what would they get as a payoff? Okay, so you can see that all those single objective and multi-objective optimization problem can be transformed to this problem, right? So now let's see what will happen if I solve this problem. Okay, consider the same example that I gave to you earlier. This is the example that I gave to you earlier, and now remember, if the weights of the players are the same, so that means, suppose that all of the players have the same negotiation powers, right? So they have the same WI. So let's say the WI for all of them are equal to 1. In that case, the Nash Social Welfare Program tries to maximize the product of benefits of each player. So suppose that D is the reference point that you have, and you solve this optimization problem. So then the objective function of the Nash Social Welfare Program tries to create a rectangle in the criterion space that has the maximum area. So this rectangle or box that I have drawn here has a maximum area, okay? And if you do that, you're gonna find this point, 3.25 and 3.5, okay? So that's the solution that you can get. So here's the magic of the Nash Social Welfare Program. So it retained a Pareto optimal point. Interesting. It is a single objective optimization problem. I just saw one single objective optimization problem. Most importantly, it retained an unsupported Pareto optimal. So it doesn't ignore unsupported Pareto optimal points. Another thing is that for this particular example that I gave to you, it was able to create to find the only fair point of the game in terms of both players. So remember, 3.25 and 3.5 was the only fair point of the game. Okay. So in the rest of this talk, let's assume that this is a simple representation of the Nash Social Welfare Program. So I just try to introduce a Y variables for simplicity. Y represent the benefit of each player, okay? Benefits of each player. So now let's see the propositions for the Nash Social Welfare Program. It always retains a Pareto optimal solution. This proposition is really important when we want to define fairness. Another thing is that the Nash Social Welfare Program is a global power scale-free. So what does that mean? That means that if I multiply the power of each player by a constant, it doesn't change the problem. So I still can get an equivalent problem in terms of optimal solution, not in terms of objective values. Also, you can see that the Nash Social Welfare Program is a local benefit scale free. So that means that if you multiply the benefit of each player independently to a constant, you're not going to change the problem. So, so this three proposition defines for you as what is the fairness. Okay. So from proposition number 2, we can see that if we have different powers, different negotiation powers, if you have equal negotiation powers, I can multiply them by a constant and assume that all of them are equal to 1. From proposition number 3, I can see that I can basically normalize the benefits of each player so that they can take values between 0 and 1. Okay. So let's say this is, let's assume that this is your f1 of x and f2 of x. And if you transform it into the y1 and y2 variables, which are the benefits that the players will obtain. So this is the problem. This is the values of your Pareto optimal solutions. And now I told you that you can actually normalize each objective values independently from each other to make sure that they're going to get the value between 0 and 1. So this is the final kind of Pareto optimal frontier that you can get. Now, let's see what we mean by fairness. So look at the solution that the Nash Social Welfare Program has obtained for us. This solution is basically has a value of 0.36 and I cannot see this, but I think that let me change. Yes, 0.36 and 0.42. So that means that these values are the ratio of the benefit of each player to the maximum benefit that they could obtain. So here, 0.36 means that player number 1 is 36% happy. Player number 2 is 42% happy, right? So because that's the from the maximum value benefit that they could get, they reach to the 42%, right? So Nash Social Welfare Program tries to maximize these benefits ratios of players at the same time, and make sure they're going to get the value of it's going to get closer to the value of 1 at the same time, and then they try to somehow make sure that these ratios, benefit ratios, are going to be more or less the same. So in fairness in this concept means that the benefit ratios of the players are going to be more or less the same, right? And they're going to be reached to hopefully to the value of 1. Okay, so that's what the Nash Social Welfare Program tries to do. So I don't want to talk a little bit about disagreement point, but this disagreement point is typically basically the status quo of the system. So that in the game theory you can select them. So basically shows that if you do not collaborate, what will happen. So let me briefly talk a little bit about like what is how we can solve this problem. I don't want to talk about the constraint set. I'm assuming that the constraint set is already handled by you. Okay. However, let's see how we can deal with the objective function itself, right? If you can deal with the constraint set, in order to deal with the objective function, you can simply use the log transformation. That's one way. Another way is to use a linearization to linearize your logarithmic function. That's another way that you can do, especially if you know that your y variables are going to take integer values. That's really good. However, perhaps one of the interesting approach that I really like a lot, and it's very effective, I can guarantee that it's really fast, so, is to transform the problem into the second order comp program, right? How you can do that? Here, my assumption is that the negotiation powers of players are integers, right? If it's not integer, just multiply them by a coefficient, by constant, to make sure that all of them, they're going to be integer. So you can transform this problem into a geometric mean optimization problem in this form. And then we have a nice transformation. This transformation is introduced by Nemirovsky and Bental in 2001. So you can transform your geometric mean into a second order comp program. So once you have created this second order comp program, you can now ask any conventional solvers like Simplex and Groovy and whatever solve this problem for you very effective. Especially the last two versions of Simplex and Groovy, they can handle this problem in a very effective way, very quickly. There are lots of other algorithms. I have developed more than 10 or 12 algorithms just on this problem. I don't have time to talk about them, but perhaps in other conferences I can go through them. And so that was pretty much the overall view of Nash Social Welfare Program that I wanted to mention to you. And I would be happy to take some questions if you have. And please consider to come to Informs Computing Society Conference 2001.
Thank you, Hadi. I think that in the interest of time, we might take your questions for after the session, and there'll be some time there for questions, and I will let Elias take it for our next talk. Thank you very much.
Thank you.
Okay, are you gonna switch the recording, Alex, or?
I am.